I probably should apologise to anybody distracted by the shirt, but it was too good an opportunity to miss to wear this. It's a lovely retirement present from some kind colleagues, and I suggested if you find any bits of the talk tedious, then you try to see what astronomical errors you can spot on the shirt. And astronomical errors are going to be quite an important part of this talk. One of the things we'll see, as Dan's already hinted, that great scientists are perhaps a bit like great people in politics. They're not people who never made mistakes or who never got or did anything wrong. It seems that scientists get remembered as great if something they did that was right gets judged to be of really serious significance and importance and a cause of great progress. So I will start by saying a bit more about Eddington, because I suspect most of us have read or heard more about Einstein than we have about the great English physicist Sir Arthur Eddington. And then I'll home in on what Eddington did to test and promote Einstein's theories, and say a few provocative things in answer to this question, how science really works. I think if you saw the advert to this talk, it was there as a sort of how science really works. I've changed it round to be a question, how does science really work? Because scientists are much better at asking good questions than we are at giving good answers. So I thought we'll hopefully say a few provocative things about that. So Sir Arthur Stanley Eddington then. He was born in Cumbria in 1882. He was the son of a school headmaster, but sadly his father died in 1884, and at that point Eddington and his mother moved to Somerset. He was born into a Quaker family and was himself a lifelong Quaker and a pacifist. And that's quite interesting because a lot of the work that I'm going to describe could have easily not happened, because as a pacifist, Eddington was claiming that he would refuse to serve in the First World War. Conscientious objectors were not well thought of at this period, and there was a real danger that he could have been imprisoned for the war, along with other known dangerous subversives, and never been able to do the work which made him famous. And it was probably due to a little bit of slow negotiation by other scientists that didn't happen. His tertiary education was at Owens College, Manchester, and then at Trinity College, Cambridge. There's a picture of him when he was reasonably young, and he was elected to a very prestigious chair at Cambridge, a professor of astronomy and experimental philosophy. He's only just 31. And in fact, it seems he was so only just 31 that there's a bit of a dispute as to whether he was appointed professor before or after his 31st birthday. So certainly quite a young star there. He has been called the father of theoretical astrophysics. So looking a little bit at what he did, he worked on the dynamics and the composition of stars. He worked on variable stars. He was responsible for working out what some of the things that make, say, Cepheid stars variable. There's one thing he's very famous for, which is now called the Eddington luminosity limit. This came about originally because he thought if you've got a large star collapsing under gravity and turning that gravitational energy into radiation and chucking that out, there'll come a point at which the pressure of radiation going out overcomes the force of gravity pulling material in, and that will be a limit to the output power that you can get from an object collapsing under gravity. Now Eddington worked that out by thinking about massive stars, but it turns out to be very important about things Eddington didn't know anything about at the time he did this work, which is active galactic nuclei. These very powerful light sources and quasars of very power sources, long way away in the centres of distant galaxies, thought now to be due to material accreting onto a supermassive black hole at the centre of a galaxy. Eddington had already worked out what limits the power that can be obtained from that system. Still a huge amount of power, but it isn't limitless. Not everything he did was right. He had a very unfortunate disagreement with the long-running disagreement, it seems, with the famous Indian physicist Subrahmanyan Chandrasekhar over the possibility for the further gravitational collapse of a white dwarf Now, a white dwarf star is the sort of star the sun is going to end up as at the end of its life. A tiny little white hot star, if it's run out of nuclear fuel and got bigger and then eventually collapsed down to a white dwarf. And Chandrasekhar deduced correctly, he won the Nobel Prize for this eventually, that you couldn't have a white dwarf star with a mass of more than about 1.4 times the mass of the sun. There's a slight variation in that because it depends on the composition of the star, but much bigger than that. And the electron degeneracy pressure, which would stop an ordinary white dwarf star from collapsing further, can no longer hold off the inevitable collapse due to gravity. And we now know that such stars collapse to form neutron stars or to form black holes. Eddington would never accept that, insisted that Chandrasekhar had just got it wrong, and I have read that that has been called one of the bitterest and I've read that referred to as one of the bitterest and nastiest disputes in physics. So it came a bit of a shock to me when I was reading to find that despite this bitter dispute, Eddington and Chandrasekhar, who also worked in Cambridge, continued to go on bicycle rides together in the English countryside, and they accompanied one another to watch tennis at Wimbledon. And when Eddington died in 1944, Chandrasekhar spoke at his funeral and described Eddington as a man of the highest integrity and character who never thought harshly of anyone. And made this interesting comment that was why it was so easy to disagree with him on scientific matters, that you could be certain he'd never think ill of you on that account. So I'm tempted to say, wouldn't it be lovely if some of the opposing protagonists in some of the other world's bitter and nasty disputes could have the respect and fondness for one another that it seems disputing scientists can sometimes have despite the disagreement. He was a man who was also, Eddington, who was also interested in philosophy, a bit of a philosopher, what we call metaphysics, I guess, and he had some ideas that we think were very strange now, and that arguably bordered on numerical mysticism. He became convinced that the fine structure constant, which measures the strength of the electromagnetic force, was an integer, something that people now would not accept. He was also a good science popularizer, and he wrote a number of books explaining the brand new theories of relativity and quantum mechanics for the general public. And if anybody's really interested, luckily, a few of these books have been recently reissued this year as facsimiles. And I read one of Eddington's Space-Time and Gravitations, an outline for general relativity theory, reproduced this year as a facsimile copy of a book originally written in 1920. And it really surprised me just how a wonderfully clear exposition of the basics of general relativity is contained in this book. And that's surprising, I think, for a couple of reasons. One is that this was written only 5 years after Einstein had first developed general relativity, and the other is the 90-some years since then, there have been numerous outlines of general relativity written that are nothing like as clear as this. So I reckon that Eddington was a pretty good science popularizer. In fact, his 1923 book, more technical, called The Mathematical Theory of Relativity, was considered by Einstein to be the finest presentation of the theorist in any language. There's a picture then of Eddington and Einstein talking together. It seems that Eddington wasn't exactly modest about his ability to understand Einstein's great many theories. When a journalist said, Sir Arthur, it said that only 3 people in the world understand relativity, Eddington's reply, yes, I've heard it, I'm trying to work out who the third person is. So moving on to the famous, or depending on your viewpoint, infamous Eclipse expedition of 1919, undertaken to test general relativity. Now, in general relativity, gravity is pictured not as a force at all, but as a curvature of space and time. And that curvature is due to mass, which then curves the space-time, and then everything moving through that curved time is affected by that curvature. And part of Einstein's great genius insight was to realise that gravity is a universal force. Absolutely nothing escapes the force of gravity. So sorry for any fans of anti-gravity drives and so on. Some things can escape the electric force or the nuclear force, but nothing escapes the force of gravity. So Einstein realised that it made more sense to picture gravity not really as a force at all, but as something fundamental to the space and time within which everything happens. Now, there's an analogy that's often done like that. I've seen it written about so many times, I thought we'd have to try it. It didn't work terribly well when we tried this earlier, and I might need another volunteer or two, please. So, what we've got here is a synthetic rubber sheet, which is meant to represent a little bit of a two-dimensional universe. And then what back up is a golf ball that's meant to represent a pulse of light, and we might use a paperweight or Dan's finger or something to try and represent this bit of space being bent by mass. Can I borrow you, Dan, or are you?
Yeah.
Are you busy for recording? I'm trying to move it. And can I? What I need is someone to grab it.
Best if we set this up here.
Dan wants to do it here. That's all right. Yes. So you can
You have to grab the middle.
As in?
Just there. Or just there, yes. Because then if you pull, quite nicely towards
Well,
you.
actually, can we do it flat first? Can
okay.
we try and get it flat? So
Am I still pulling?
We get out at the edges and try and get it nice and flat. And then what I demonstrate is that with it flat, that golf ball runs in a straight line. So that's a pulse of light moving in a non-curved universe. Now, yes, do you want to, how do you want to
just slightly lift it? Do you want to just put your finger down where you think you want your gravity?
So we have our force of gravity there. And now if I roll this golf ball, due to the curvature of light, it bends. So the idea was that that could be measured. Is that, are you happy with that?
Yep.
Thank you. That's I've never seen that done. I've read it in a book so many times. Let's give it a go today. Thank you for your help and patience. So in theory then you can measure that deflection. There is, by what you do is you look at the light from a distant star which has come past the edge of the sun and you try and detect that bending due to the curvature of space and time near the sun. Obvious problem, you need the light to come past the edge of the sun, and if the light comes past the edge of the sun you can't see any stars because the sunlight blocks them all out, except of course during a total solar eclipse. So the idea is that you can do this during a total solar eclipse. And after Eddington'e proposed to the Royal Astronomical Society that it was very important to try and do this test, the Astronomer Royal at the time, the guy, if I remember rightly, called it Frank Watson Dyson or something like that, realised that the eclipse coming up on the 29th of May 1919 was ideal, as the well-known Hyades star cluster would be well placed in the sky to do this experiment with that eclipse. So here's a little drawing actually from NASA to try and show the idea. So here's a distant star, and here's some light from the star coming along. Now if it didn't go anywhere near another massive object, that light would just go on in a straight line. But the sun is in the way, so as the light goes around the edge of the sun, and goes near the sun, it's bent down onto Earth, with an observer on Earth looking at that light, looks back and sees a star as if it was there, not there. Now I have to say that effect is enormously exaggerated on that drawing to make the point that it's also enormously exaggerated in that little demo. But sticking with the exaggeration at the moment, that this rectangle at the bottom here shows the actual star field that you would observe when the sun was nowhere near, and this shows what happens when you put the sun in the way. And you see that the stars near the sun, where the light has come close to the edge, now appear to have moved further out because of that deflection. You also note that stars far away are unaffected because their light hasn't come particularly close to the sun. So that's the idea of Eddington's famous experiment. There were a few problems, like the eclipse wasn't anywhere convenient to see the total eclipse You couldn't see it from England. You have to be in South America or Africa. And there were 2 observation sites identified, one in Brazil and one in a tiny island off the west coast of Africa, which was under Portuguese control at that time. I'm trying to avoid saying the names, so I'm not sure of my pronunciation, but I'll have a guess it's something like Sogal and Principe Bay, and if anybody knows any different, please correct me. Why was this test difficult now? Quite apart from little man-made difficulties like the fact that there was the First World War going on when Einstein was working, and Eddington, as a scientist working in England, had no access to the results of Einstein working in Germany, although luckily down through Willem de Sitter, who became one of the founders of cosmology, who lived in neutral Holland and was able to pass Einstein's papers on to Eddington. But quite aside from that and the odd threatened strike of steamship operators causing expedition travel problems, there are a lot of technical issues. To start that off, I'll first of all put up this little quote. Do not bodies act upon light at a distance, and by their action bend its rays? And is not this action, something from the Latin, strongest at the least distance? And just in case you think that's an obscure bit of writing by Einstein, that's actually taken from a treatise on optics, or a treatise on the reflections, refractions, inflections and colours of light, written by Isaac Newton and published in 1704. And there is the big catch, that even in Newtonian theory, light will be bent as it goes past a massive object. It's not just relativity that makes this prediction. The difference is in the size of the prediction. And it turns out that relativity predicts exactly twice the amount of light bending that you get from Newtonian theory. Now, I put Newtonian theory in brackets because it does depend how you think about light. If you think about light as a wave or a zero rest mass particle, you could argue it shouldn't be bent. If you accept that E equals mc squared, which is a result from special relativity, which didn't deal with gravity, then you can argue that light carries energy at certain some mass. It's clear from things like radiation pressure that light can be thought of as momentum. And just accepting that and doing a sort of Newtonian ballistics calculation, you calculate that light will be bent. I don't know if any of you saw that drama documentary that was on the BBC a few years ago about Einstein and Eddington. It did a lovely job of showing that the human side of this very interesting human story, but it horribly misrepresented the science. At least broke up so often. Because what happened is that at some point Eddington looked down the microscope to compare the photographic plates and looked up and said, they've moved, the stars have moved. And the mere fact that the stars have moved position was enough to prove Einstein right and Newton wrong to all the assembled scientists. It was just never ever that easy, it was never ever going to be. So for one thing, it wasn't just a question of whether the light bent, it was a question of how much the light bent. And to make it worse, the amount of deflection is tiny. Less than 2 seconds of arc only predicted by general relativity, and only half of that by Newtonian theory. So you've got to distinguish between those 2 very small angles in making these measurements. Now, just to set that in some sort of context, because if you're into astronomy, you might be used to thinking about that sections, but just to remember what something is. You've got a pound coin, and you take it out of your pocket, and you hold it at arm's length. Then the difference in angle between looking at the bottom of that pound and looking at that top of that pound, the diameter of the coin away, is something between 1.5 and 2.5 degrees. Probably a little bit less than 2 degrees, unless you've got particularly long or particularly short arms. In order to get that angle between the light from the bottom of that coin and the top of that coin to be 2 seconds of arc, you'd have to give that coin to a friend and have them walk away from you and keep on walking away from you. And when they were about 1.5 miles away from you, at that point that angle would be 2 seconds of arc. So that's the angle that they had to try and measure and distinguish between that and something half the size. Now, astronomers can measure those sorts of angles and have been able to for ages, but they normally do it using nice telescopes and observatory domes that are all properly maintained It's harder to do it with portable equipment. To make it worse, they've got to do all these measurements within the time of a total eclipse. And no total eclipse can be total at any one spot on the Earth's surface for more than about 7 minutes. So that was all the time they got to expose their photographic plates and make the measurements. That meant they got no time to do what astronomers normally do, which was to allow for the telescopes to adjust to changes in temperature and settle down and thermally calibrate. The exposure times were no more than 20 seconds, but even in that time, the stars would move a bit in the sky due to the Earth's rotation and just appear as streaks on the photograph, which is the last thing you could cope with. So they have to compensate for that. Again, astronomers are used to doing this by tracking the telescopes to counteract the Earth's rotation. That's hard to do in strange foreign islands and so on. So what they did instead, which was standard practice for eclipses, was they kept the telescopes, as Dan was saying earlier, very long focal lengths, 19 feet or so, for telescopes to do solar observing. They kept the telescopes stationary, but they used a clockwork-driven mirror to track and reflect the light into the telescopes. And there was one other problem that they had to contend with, which almost got you this afternoon. I'm glad it was quiet. Weather. You might think in the southern hemisphere what you've got to worry about, well actually the weather at that West African island was lousy, and we almost didn't get any results at all from that too. So in short then, there were a lot of technical challenges and possible causes of measurement inaccuracy which had to be corrected or allowed for. Some serious causes of systematic error which would have thrown all the results out by an amount greater than the angle differences they were trying to measure. And the best way to compensate for that was to take check plates, photographic plates of the same stars, but with the sun nowhere near. And the way to do that really was to take those reference plates at the same observing location, and preferably when those stars were in the same position in the sky, but the sun, it was night time and the sun was nowhere near. Sadly, it wasn't possible to properly do that. So this was always going to be difficult. So here's a picture of the equipment, actually from a copy of the front page of that book. That's a long telescope with a 13-inch astrographic objective, which they stopped down to about 8 inches for the measurements. This only there at the Brazilian site was a 4-inch telescope we used as well. These are the two mirrors that reflected the light into the telescopes, and that's the clockwork motor that rotated the large mirror. So that's what the apparatus actually looked like. That is a negative of one of the photographic plates. It's a negative, so what on this little thing is an eclipse sun in dark with a little bit of light left around the edges. Is here a bright spot in the middle of the eclipse sun, and the light around the edges is the dark bits. And if you've got much, much better eyesight than me, you can perhaps see a few of the dark dots on that plate with the stars. And if you've got incredibly good eyesight, you can perhaps see a couple of little marks where Einstein, not Einstein, Eddington, put indicators around stars that he thought they could use to make the measurements. So you get the idea, this was difficult. So before we look at those results, let's ask a few contentious questions about this topic of how science works. Here are some possible answers. A very naive view of how science works, which is sort of sometimes what skilled pupils are told to begin with, is that it works by scientists formulating hypotheses, which are then tested by experiment. Now, there's obviously some truth in that, but in the most naive version of this idea, the experimental tests are completely objective, they're independent of any theory, they're not dependent on any context. It's very clean and easy. The philosopher of science, Karl Popper, said that science progresses by refutation, by things being proved wrong. No amount of experimentation can ever prove the theory right, because to prove a theory right in all circumstances, you'd have to do all possible experiments. But a single experiment can prove a theory wrong. So the Karl Popper, an essential feature of a true scientific theory is that it is falsifiable. And he was very impressed by general relativity, precisely because it did make predictions that could be tested and could prove the theory wrong. I'm sorry that I've probably got a bit more material here than I really go through properly in the time, but I have got some handouts of these slides if anybody would actually like those, any detail that I've gone through really quickly. There are other ways in which science might progress. It might progress by scientists just picking the theories they think are the most beautiful, in which case general relativity is one of one's hands down. There are some lovely examples. There's an old Greek saying, if it's beautiful it must be right, but there are some good examples in astronomy of very beautiful theories sadly being proven wrong. The philosopher of science Thomas Kuhn pointed out that science tends to work by long periods of what he calls normal science, where nothing terribly exciting happens, existing theories get applied to more and more things, you know, the loose ends get tied up, and then short periods of scientific revolution, where the scientific community decides fairly quickly that, okay, the evidence has now built up to a point where they will fundamentally change their view of the world. And this Kuhn referred to as a paradigm change. There are, of course, some more cynical views. The conspiracy theorist view, there's no such thing as scientific truth, it's just a story that all these scientists conspire to tell the global public. I'm not going to argue for that, but having said that, part of me has a sneaking suspicion that there's some truth in the old saying there are no such things as theories being rejected and dying in physics, and it's just old scientists who eventually pass away and a new generation comes along with minds more amenable to different ways of thinking. So going back to that first one, and the naive view, that the experimental tests are completely independent of theory, so they're nice and clear cut. Science at its frontiers is really that straightforward, and that's pretty obvious in astronomy. If you think about something as basic as measuring distance, how do we measure the distance to a distant galaxy? We ain't going to get the tape measuring up from planet Earth and go to a distant galaxy at the end of the line. So how do we measure that distance? And the answer is that we do it by measuring properties from that distant galaxy like lighting and stuff. But of course, to then interpret those results, we have to assume a whole pile of theory. And if any of that theory is wrong, then our measurement of distance is wrong with it. You can't actually untangle theory and experimental observation entirely in the way that it would be nice perhaps if you could. Another example that struck me a while ago is a really fascinating one. It's an experiment which is in the textbooks as one of the early proofs of relativity, a special theory called the Michelson-Morley experiment, actually done before Einstein, originally done for a very different reason, done to try and measure the speed of the Earth through this amazing stuff, the all-pervading luminiferous ether. In the days when it was realised that light was a wave, but not realised that light could travel through a vacuum, people thought the light must be a wave in something, and that the universe was filled with this something, and they called it the all-pervading luminiferous ether. And the Michelson-Morley experiment tried to measure the velocity of the Earth through the ether, and to the surprise of the scientists who carried it out, completely failed to detect any velocity of the Earth through the ether at all. Now, we know that that's because there is no ether. The scientists at the time the experiment was done already knew that the Earth moved in orbit around the Sun, but just suppose that experiment had been performed in 1633, which is the year when the Roman Catholic Church was having a real problem with the heretical Copernican views of Galileo. Wouldn't it have been seen then rather differently? Wouldn't it have been seen as clinching proof that Galileo was wrong and the Earth did not move? But the context and theory have moved on where it was actually performed. So it's hard to separate experimental test and observation from theory and context. So what should scientists do when the data don't match the theory? Should they dump the theory or should they dump the data? Be warned if you want to jump in. You can't win whichever way you answer this one. It's easy to say scientists should never dump data. That's most disreputable. Science should be driven by data. I'm actually a little bit bemused that that phrase data-driven seems to have become part of modern senior management speak. Being data-driven is something that senior managers are whilst going forward, if you've heard phrases like that, which bothers me a bit because so many senior managers in this country seem barely numerate, let alone capable of distinguishing good data from poor data or making intelligent conclusions based on analysis of complex data. But the point is that there is such stuff as poor data. Data can be affected by, it can look superficially precise, but be affected by problems that make all the measurement wrong in one direction. And one of the jobs of being a good scientist is to realise when that's happened and dump that data. Theory can sometimes be wrong as well, of course, so sometimes you need to dump theory. Sometimes both are wrong, sometimes neither are wrong. Nice example from astronomy. In 1846 it was known that the orbit of Uranus didn't fit Newtonian theory. Rather than dumping either Newtonian theory or dumping the data, the astronomers Adams in England and Leverrier in France accepted that both were still true and found the planet Neptune as the cause for the anomaly, so they found the new planet. Unfortunately, when later on astronomers tried to take the same approach to explain a little discrepancy in the measured orbit of the planet Mercury, by assuming that that was due to an as yet undetected planet, which they actually called Vulcan, well, they never did find Vulcan, and as we now know, nobody found Vulcan until one of its inhabitants got a job on the Starship Enterprise. But actually, the explanation there is that Newtonian gravity isn't quite right, and the discrepancy between that and general relativity is most noticeable for Mercury, because that's the planet nearest the Sun, where the curvature of space-time in the solar system is at its greatest. So here are the results then of Eddington's expeditions. The general relativistic prediction for the bending of light passing the edge of the Sun was 1.74 seconds, and the Newtonian one exactly half of that. Here are the results. I don't expect you to look in detail at these figures, but things to notice are mostly here that Eddington openly admitted to having dumped a load of data came from numerous poor plates taken with the main telescope from the Brazilian site, which he freely admitted gave all too good agreement to the Newtonian value, but which he rejected, mainly on the grounds that the image was distorted. They thought there had been some temperature effect on the mirror, and there was a lack of proper check points. Here's a reanalysis of the same results made by Ian Leimer and discussed by Collins and Pinch in their book The Golem, What We Should Know About Science. Their first version of the book was called What Everyone Should Know About Science, so I'm not quite sure why they changed their subtitle. This includes the analysis from the 18 poor plates from Brazil that Eddington rejected, and yes, they certainly do look like good confirmation of the Newtonian result, not the Einstein one. So in terms of the conclusions, Eddington's conclusion, the expedition quantitatively confirmed Einstein's prediction. The conclusion of these people, it was very difficult to provide a clear answer based on this data. You couldn't draw a clear conclusion from it. I just want to read just a little bit of what Collins and Pinch say about this in their book, The Golem, where they say, although there are other reasons to believe Einstein's value, the evidence for the bending of visible white stars confirming his theory, at least up to 1952, was either indecisive or indicated a value too high. And yet 1919 remains a key date in the story of relativity. Is this because science needs decisive moments of proof to maintain its heroic image? None of this is to say that Einstein was wrong, or that the Eclipse experiment wasn't fascinating and dramatic. But we should know just what the experiments were like. The picture of a quasi-logical deduction and prediction, followed by a straightforward observational test, is simply wrong. What we have seen are the theoretical and experimental contributions to cultural change, a change which is just as much about a license for observing the world in a certain way as it is a consequence of those observations. Interesting comment, and that from people who are, I have to say, pro-science. I haven't really got time to read you Eddington's long justification for doing what he did. it would shock some people to read how freely and openly Eddington admits to not having been an unbiased observer, but to having gone expecting and hoping to find the value predicted patterns. So, I would just say the debate still rages. There was a paper published only a few years ago saying Eddington is innocent and saying that he did make the right decisions based on the data back. The aftermath of this was amazing. Here is a sort of tabloid newspaper type headline in the New York Times in November 1919. Men of science more or less agog over the results of eclipse observations, lights all askew in the heavens, Einstein theory triumphs. The Illustrated London News was much more helpful and informative, and gave a really nice graphic of what the experiment was about and what the apparatus looked like, and so, you know, an altogether high quality publication, obviously. There are some arguments about the conclusions. They are presented by the Astronomer Royal, backed up by Eddington and another scientist, in a joint meeting of the Royal Astronomical Society and the Royal Society. Somebody stood up and pointed at a picture of Isaac Newton that was hanging on the wall and said, we owe it to that great man to think very carefully before retouching his theory of gravity. The chairman, J.J. Thomson, who discovered the electron, pronounced it the greatest advance in gravitation since Newton had lived, and there was all sorts of debate as to whether Eddington had given them enough information to decide for themselves, whether they should just trust what the Astronomer Royal Eddington were telling them. It was all very contentious. And Einstein became a household name. Perhaps he was the first celebrity scientist of modern times. Some of the things that followed from that are amazing. He was invited to become the President of Israel. He wisely declined the offer. He was invited to appear in a variety show at the London Palladium. You can sort of imagine the compare, you know, and now to follow from Ken Godin's Didymem, where you put your hands together for Albert Einstein with his mathematics. You know, you just can't imagine what they expected him to do. But that was what this fame brought with it. And Eddington became famous as one of the leading proponents of Einstein's theories. Here's a stamp from to celebrate the 90th anniversary of the expedition. I think it was a Portuguese one because it was at the Portuguese colony. So, whether the data did or didn't justify the conclusions, you can sort of read more yourself and make your own minds if you want to. Were the conclusions that Einstein was right and Newtonian theory wrong correct? Well, I guess if it hadn't been, I wouldn't be here giving this talk now. But it actually took a long time to show that convincingly from light-bending experiments. There were other ones, because they remained difficult. It was only really when it became possible to make these measurements using interferometric arrays of radio telescopes that it became much easier. Because if you work in the radio and look at powerful radio sources, the signals from them being deflected as they go past the sun, you don't need to wait for an eclipse. You don't even need to wait for fine weather. You can do it whenever those sources pass close by the sun. And that's probably provided the best verification of the Einstein predictive value for the bending, much better than has been obtained and visible. The question is, were there other good reasons for believing the Einstein value, even if you've never done the experiment? Well, Einstein was asked how he had felt if Eddington's expedition had proved that Newton was wrong, so that Einstein was wrong and that Newtonian theory was correct. Einstein's answer, I would have felt sorry for the good Lord. He would have felt sorry for a creator God who failed to realise that the universe had to be made to fit Einstein's theory, not Newton's. Sounds incredibly arrogant. Might have been, I imagine, tongue-in-cheek. Was it because Einstein thought his theory was too beautiful to be wrong? Or was it because there's something perhaps even deeper? If you look behind all that mathematical sophistication of general relativity and say, what is this theory really based on? At heart, it's based on little more than a very old idea that the laws of nature should be something that all observers can agree on, no matter where in the universe they are, or so on. Now that's clearly something that we can never test. We can never go to another galaxy and check that the laws of nature are the same there as they are here. We have to take it as an assumption. If included in the laws of nature are the known laws of electromagnetism, then you almost inevitably end up at something pretty like general relativity, from very little more than the assumption that universal laws exist and that we know some of them. So you can have sympathy for Eddington and Einstein feeling that the universe has to be this way, otherwise we can't make sense of it at all. So what lesson can we learn from all this? Well, certainly the real science is much more messy, much more human activity than it's often portrayed to be by the media or by the textbooks, which do tend to pick up an experiment like this Eclipse one and leave aside all the difficulties and arguments and just cite it as something that showed that relativity was right. And it was never quite that straightforward. I'd like to argue that we should accept that scientists are neither saints nor Daleks, by which I mean that scientists are not divine beings with some hotline to an indisputable truth that's hidden from other people, and nor are they beings devoid of human feeling but out to exterminate or dominate. And I personally think it's very dangerous for society, democracy in the world, if it's generally thought that science and scientists are either intrinsically bad and up to no good and can't be trusted, or that they're infallible. If science is perceived as infallible, then people do silly things like believe we can carry on polluting the planet and that some scientists and future generations sort out all our sins for us and so we don't need to worry. If people believe that science is infallible, then eventually they get disillusioned and we get a backlash against science, which I think we've seen in our lifetimes, we're only just pulling that off. And that was bad as well, and that leads to science being perceived of as intrinsically bad and not to be trusted. And the problem with that is if you look at the things that people trust when they don't trust science, actually a great deal less to be trusted, and people who completely turn their backs on science are at the mercy of all the quacks and cracks and political spin doctors, and inclined to believe that the opinions of either pop stars or footballers on important matters of science and technology and the environment are as valuable as those of the scientists who devoted their lives to becoming genuine experts in these fields. And that, I think, is truly dangerous for democracy. Now, I've got a couple of more slides down. Should I stop or should I carry on? So just to come back a little bit more specific, trying to be provocative, I thought, are there any more recent experiments that might get looked back upon in time in the way that Eddington's Eclipse expedition is looked back upon now? Something that came to the right conclusion, but there's a doubt as to whether there really was the data to justify it. And I'm going to very naughtily suggest maybe the recent supernova experiments, which quite rightly won the people who performed the Nobel Prize the other year, and that showed that rather than the universe expansion slowing down so the universe might one day stop expanding or even contract, the expansion of the universe is speeding up. Now, those measurements are similarly difficult in modern terms to Eddington's Eclipse measurements. The effects that you're trying to see are smaller than the corrections that you've got to make to the data. It's very difficult to do and get it right. Have those results now been accepted simply because the data are so compelling, or is it just that this is an idea whose time has come, maybe to quote the words of a London cosmologist, Bernard Carr, cosmologists have been saying for years that we're going to need a little bit of cosmological constant in there, pushing the expansion ever faster to make models work. And so this is a paradigm shift going on in our time. And cosmologists have stopped asking when will the universe recollapse or will it recollapse, and started wondering why the expansion continues to accelerate. And it's interesting to take the links back with what we've been looking at, because the supernova used in these very difficult, more recent measurements are a supernova type SNE1A, which are the type of supernova that occurs when there's a white dwarf star in a binary system and it's accreting material for a companion star, and when it gets to 1.4 solar masses, it implodes. Just like Chandrasekhar said it was, and produces a supernova, which is perhaps the best standard candle that astronomers have got. It's not perfect, but it's the best we've got. So credit to Chandrasekhar for his work again, then being picked up very recently in this very exciting new way. Interesting too to note a link back to Eddington, because once Hubble and co had shown that the galaxies were moving away from us and the universe was expanding, a lot of people felt the cosmological constant term in the field equations of relativity could then be dumped. It's alleged that even Einstein once referred to that term as his greatest blunder, putting it in the equations, which seemed an odd thing for him to have said because it arises there quite naturally. But certainly, once it was known that the universe was expanding and we no longer needed this term in the equations in the attempt to make a model of a universe that didn't expand on track, most people thought that that term in the equations could now be dumped. Not Eddington. Eddington disagreed with dumping the cosmological constant. He called it the cosmical constant in those days. I guess at some point somebody thought cosmical is just a bit too close to comical, maybe we should call it something else. So it became known as the cosmological constant. But Einstein said it renders the whole theory so much more meaningful and complete to leave it in. And I think that there's another bit of insight and foresight for which Eddington deserves a great deal of credit that I really heard him get. So that I really must stop because I've gone way over time. Thank you. I'm happy to not answer any good questions or indulge in any debate about the nature of science.
Are there any questions for Robin?
I thought the idea about data and the validity of it was very interesting, because you can apply that to very many things. For example, the expansion of the universe and Hubble's original.
Yes,
as one example.
Those measurements are also contentious if you look back at them. You know,
how do you draw a straight line?
How do you draw those straight lines? Yes, so maybe Kuhn, had a point that it isn't a simple matter of experiments verifying or falsifying theories. The body of evidence suddenly becomes taken as a reason to change the viewpoint, and then things are justified with hindsight.
I thought you were going to give an example of the Higgs boson.
I don't. I don't know enough about it to comment. Who knows?
You mentioned you had to observe with 2 arcsecond precision to get the data for the relativity.
Yeah, I mean, they have to do better than that.
Do better than that, even, yes. What's the typical seeing they had encountered?
I don't know.
Because normally, if we think in Nottingham about seeing 2 arcseconds, we would be over the moon. That's quite good.
Yeah, I mean, they had got the sites that were good sites for astronomy. But it's perverse because it seems that the Brazilian expedition had the clearest sky, but they got very fuzzy images from the main telescope. And Eddington certainly thought that that was because they calibrated during the night, and then in the daytime the equipment expanded and things went out of focus. I don't know whether they tried to recorrect. But then, of course, the eclipse came along and the temperature plummets during an eclipse. So the thermal stresses in that big telescope were all over the place, and that's probably why they struggled. Perversely, because of the bad weather at the African island, they didn't have that temperature variation. Eddington says the temperature variation at that site was within 1 degree. But the trouble was they had clouds in the sky, so they didn't win either. And they put a lot of faith on the data of that 4-inch telescope. Eddington did say that for the main plates, I don't know about the 4-inch ones, these were old-fashioned photographic plates. And the distances they were trying to measure corresponded to 1/1500th of an inch, which I mean is a reasonable distance to measure with a microscope on a photographic plate. But you've got to ask all sorts of questions about the possible expansion and contraction of that plate during the exposure, the uniformity of the photographic emulsion and so on. One hell of a challenge. And
what is your personal opinion then regarding, you're talking dumping data, dumping theory, or treating data as the truth and never dumping data?
I think you have to look at each thing in their context, and I think the problem is that it does take somebody who is a real expert to make a sensible decision as to whether data are valid or not. And it is very difficult then for that person to do that wholly objectively, because they often do have a feeling as to what the results should be. There are all sorts of examples of this, but you can't take that aspect, that human aspect of science away. I think it's a bad mistake to deny it. It worries me when, people are told that there is such a thing as a scientific method and it's infallible if you just follow it. That's just not, it's just not that simple.
So who's the expert then? Because you said you need an expert to decide, but in this case it must have surely been Eddington'e, Einstein, who are the ones that wanted to prove their theory. So yeah, you're asking the ones proving their theory to see that...
Where were the counter-experts who got a chance to look at the data? That I think is a good question.
And the other thing that I like quite nicely is that you need a feeling for this data. So in this case, this is something that has no number attached to it.
Yep.
Nothing frequency-wise, you can't measure it, you can't fathom it, it's a feeling. So
based on experience, very, 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 very worrying for people trying to develop expert systems, to replace all the doctors and something. People like me are saying that actually look at great science and it works in part by human feeling and intuition that is very, very hard to quantify and codify. I'm a little bit reassured by that rather than frightened by it, to be honest. But another classic example is the famous Millikan-Aldrich experiment to measure the charge in the electron, where it's reckoned that if you look through his notebooks, he did this experiment hundreds, if not thousands of times, and published only a few of the results, having scribbled things in the margin like, this is a good one, I must publish this. And you say, how did he know? That was the one to publish.
An interesting point would be, would you believe the data of the Eclipse?
I must admit, I've changed my mind several times preparing for tonight's talk, and I'm still not sure whether I think... I think there was a paper published in about 2005 in Nature, I believe, by somebody who said Eddington was innocent after all the fact. If you really look with the best that we can do with modern data analysis at his original data, his arguments actually do stack up. I haven't really gone in to that level of detail look myself. It would be foolish, I think, to comment. It's not clear cut. Maybe no one will ever agree.
What's your feeling?
But I mean, I think my feeling is that he was biased as hell, but probably justified in doing what he did. But I also think that he was pointed out that science is not a straightforward, objective process. It's portrayed to have a point that really should be listened to, and science needs to be. I would say science and scientists need to be honest, but I think the problem so often is not the scientists themselves. It's the media reporters, it's the people who then write the textbooks and suddenly give somebody's experimental results a level of certainty that the scientists who actually did those experiments would never ever have claimed. And that, I think, is where part of the problem comes from.